So if we're going to look at the quantitative side of chemistry, we need to start with our smallest particles, the atoms. So we have atoms of each element. And it's been long known the relative masses of the different elements. And they used hydrogen as the basis for this in the beginning. So they said the hydrogen had a mass of 1 unit and everything else was relative to that. Later on, they changed to one of the isotopes of carbon, carbon-12, and they used that as the base unit for the measurements. So the isotopes of carbon are carbon-12, carbon-13, and carbon-14. So carbon-12 was defined as having a mass of 12 atomic mass units. So not very creative, but it actually makes it easier for us to remember. So given that a sample of carbon then has a mixture of these different isotopes, the average mass of one atom of carbon is 12.011 AMUs, atomic mass units. So we're going to put our masses down this column right here. Obviously, a single atom is much smaller than what we could ever measure with any of our instruments. So what if we go with a larger number? Well, we could go all the way down to, say, 1,000 atoms of carbon. So 1,000 atoms of carbon would be 12,011 atomic mass units. Okay. Again, an amount that's way too small for us to measure with any balance that we have available to us. So let's keep going. Well, what if we go to 1,000,000 atoms of carbon? So now we would have 12.011 times 10 to the 6th, or 1,000,000 AMUs. Okay. Still not enough for us to actually measure a sample of carbon on a balance. Well, we need to kind of rethink things now. Instead of going up with just the round numbers of carbon atoms, let's take a look at the mass. And this is what a man by the name of Avogadro, he said that, well, let's take a number that works out with all of these, but that's in a unit that's large enough for us to measure on the balance. So 12.011 grams. So notice that we have the same number, same digits, but we have a different unit. So an individual atom of carbon, 12.011 AMUs for the average mass. And how many particles would this correspond to, to get to 12.011 grams? So this is where Avogadro came up with a number, and this is known as Avogadro's number. And that number is 6.022 times 10 to the 23rd atoms of carbon would have that mass. And it turns out that if you take any of the elements and you mass out their atomic mass, their relative masses in grams, you would get this exact same number. So this number then is given a special name. Chemists refer to this as a mole. So 6.022 times 10 to the 23rd is referred to as 1 mole of carbon, or 1 mole of carbon atoms. Now, we have plenty of analogies to this in real life. We go to the baker and we order a dozen bagels instead of ordering 12 bagels. We might go to an office supply store and order a gross of paper clips instead of saying we want 144 paper clips. So this idea of some other unit that represents a larger number of things isn't totally new to us. We've done this before. So now it's just a matter of doing some calculations with this and understanding how we can apply this to the quantitative measurements that we might make in the lab. So here we have a few examples, and we're going to use our dimensional analysis technique to solve these. So the first one is, how many atoms of carbon are there in a sample with a mass of 5,080 AMUs. So we would take our number we're starting with, 5,000 AMUs, put that over 1, and put the AMU on the bottom. Now, I should probably be a little bit more clear here. It's AMUs of the element carbon. And so then we want to go to atoms of carbon. So we know that the average mass of an atom of carbon, so one atom of carbon, is 12.011 AMUs. So to two significant figures, that would be 480 atoms of carbon. We should probably cancel out our units here. Now, compare that to the next one, where we have how many atoms of carbon, so we're figuring out atoms of carbon, are there this time in a sample with a mass of 1.00 grams. Right, so now we're going to start with 1.00 grams of carbon over 1. So we've got grams of carbon down here on the bottom. But we can't go from grams of carbon to atoms of carbon. We can go from grams of carbon to moles of carbon atoms. Right, that was the conversion that we saw on the last page down here. Right, we have 12.001 grams per 1 mole of carbon atoms. So 1 mole of carbon in the atom there, 12.011 grams. Now this gets us into moles of carbon atoms, but if we actually want to know how many individual atoms there are, we would then have to go from moles of carbon atoms to actually atoms of carbon. And 1 mole of anything, so this number is like the dozen number, is 6.022 times 10 to the 23rd. And so to three significant figures, we would have 5.01 times 10 to the 22nd atoms of carbon. Again, so we converted from grams to moles, and then moles to atoms, or moles of atoms to actual atoms. Okay. So let's try one more. What is the mass in grams of 3.0 moles of carbon? So again, we're going to put our 3.0 moles of carbon, and we're going to put that atom part in there, times, so we got moles of carbon atoms on the bottom, and we want to go to grams. So we can do this. We can go directly to grams of carbon. 1 mole would be 12.011 grams. And then we have our moles cancel out. So to two significant figures, we have 36 grams of carbon. And again, it's just going to involve doing some practice. Now, most of the reactions that we do aren't going to be single elements reacting. Usually we have compounds. So we need to figure out how to work within compounds. So let's try that on the next couple of problems here. So the first one is, how many molecules of water are there in a sample with a mass of 5,080 AMUs? All right, so if we did the 5,800 AMUs, but this time we've got water over 1, and we want to go from AMUs of water. So again, that's just a mass unit. So it's just an amount of water. And we want to go to molecules of water. All right, so how are we going to do this? Well, a molecule of water is made up of 2 atoms of hydrogen and 1 atom of oxygen. So if I look at the periodic table, each atom of hydrogen, so I've got 2 hydrogens, right? And each atom of hydrogen has a mass of 1.007. So what we're going to do is we're going to take that 1.007 and we're going to multiply it by 2. And then there's 1 oxygen, so it would be 1 times the 15.99999. And we'll be able to round these to 1 decimal place. So you don't have to worry about using up all of these. So we add this together, we're going to get to 3 significant figures, 18.0 AMUs for the mass of 1 molecule of water. So we have 1 molecule of water, 18.0 AMUs. So the AMUs of water cancel out. And to two significant figures, we would have 320 molecules of water. So again, the only thing that's new here is this part right here, where we needed to, figure out the mass of a molecule by adding together the individual atomic masses of the atoms that make up that element. So we'll try using the conversion in just a slightly different way. So here we want to know the mass in grams of 3.0 moles of water. So we've got 3.0 moles of water. And, when we talk about moles of water, we're talking about, the smallest part of it as a molecule. And we're going to put that over 1. So we want to do moles of water we want to go to grams. So how do we go from moles to grams? Well, if we look back over at the last one, we did this in the last problem here, right? We went from moles of carbon here to grams of carbon. And so we just used that mass, the average atomic mass, but in grams for the mole. So we're going to do the same thing here. Above, we figured out that the mass in a single molecule of water is 18 AMUs. So down here, the mass of 1 mole of water molecules is going to be 18.0 grams. So the moles cancel out. And then we get an answer of 54 grams of water. So what we're going to do is do a lot of practice with this. But here you saw some of the different types of calculations you would do with this. The conversion factors, again, are like tools. So you use a dimensional analysis technique, and then each conversion factor is like a tool that helps you get from one unit to another.